Hello, this is the automatic soccer ball kicker and retriever. Our project charter was to design and build a two-part robotic system composing of a angled wheel-driven launcher and a retrieval unit that autonomously collects and reloads the soccer ball, all within a completion date and a budget.
So here are our Team 6 members. My name is Mia Baltrin. My major is electrical engineering, and I plan to work as a control systems engineer at Ford Corporation.
My name is Daniel Castro. I major in electrical engineering, and my current future plans is to be an applications engineer at Altec Incorporated.
Hi, I'm Jake Greenlee. I'm a computer and electrical engineering major. My future plans is to work at Club Car as an electronic controls engineer.
My name is Riley Reinhardt. My major is electrical engineering, and my future plans are to work as a transmission project engineer at Booth and Associates.
I'm Ethan Schneider, and my major is electrical engineering, and my future plans is to work as a transmission planning engineer at Duke Energy.
I'm Garrett Smith. I'm majoring in electrical engineering, and my future plans are to work in the power industry.
So to begin, our project motivation is to create a hands-free soccer training system that reduces soccer ball retrieval during practice, and this increases training consistency for the user by giving them repeatable and controlled ball launches towards them. And in total, this demonstrates how robotics and automation can increase efficiency in sports. And the overall goal of the project was to develop a working prototype. And as for our milestones that we set for ourselves, milestone one, we wanted to just get the chassis built for our robots. Milestone two, we focused on individual part testing. And then as for our final deliverable, we integrated all the systems together and had a complete system.
So here's our project implementation. As you can see on the left, here are two pictures of our launcher unit, and on the right side is a picture of our retrieval unit all put together at the end. And then here's a block diagram breakdown of the hardware. In the soccer ball, we used Bluetooth beacon in order to communicate with the retrieval bot. This is using trilateration. Trilateration is a process in where we take three distance vectors using RSSI and DBM calculations in order to determine a grid location for the soccer ball that we can drive towards to capture and return it. In the capturing process is the retrieval or receiver bot that we use that has a 9 degree of freedom and time of flight sensor, as well as a camera and servo motors and DC motors, all that are communicating and used through the Raspberry Pi that use the image processing and controls in order to complete its task. And then lastly, the major part of our project was the launcher bot. This uses Bluetooth communication with the receival bot in order to determine when it should turn its launching motors on and off. It also includes these launcher motors to turn them and make sure they're up to speed, as well as linear actuators that we use to set the launch angle as we set in our requirements. And here's a brief flow chart of our project. This all starts with user inputting the launch angle, motor speed, number of launches, and the time to wait before launching. And then it goes into a large loop confirming if there's still launches left to be achieved. If so, then the two launcher and retriever bot must communicate between each other to make sure it's at the correct speed before it feeds the ball. Once it feeds the ball, the receiver bot waits and uses trilateration, camera, and computer vision, and the time of flight sensor in order to retrieve the ball. And then after that, it will return back to its original point to restart that entire process. And then when it's completed, it turns off both bots in order to preserve power. And some of these requirements laid out a little bit more in depth is in the retrieval bot. Be able to detect ball location using these processes we already talked about, and drive to and grab the soccer ball and return the ball back to the kicking station with a high level of accuracy. For the launcher robot, we need to be able to accept the ball through the guided rail system, as well as launch it with 100% accuracy and have customizable user-controlled angle control through our GUI for this angle control and launch power. And then lastly, for our custom soccer ball, we needed to embed a Bluetooth low energy beacon within the ball for the detection.
So here we have a breakdown of the retrieval robot hardware design. We used two DC motors as well as a dual channel motor driver for movement. We used two servo motors for ball grabbing. We used a camera for ball detection as well as a time of flight sensor for proximity detection and a 9 degree of freedom sensor for trilateration. We also used a 12-volt battery as well as three buck converters, and then we had a 3D printed chassis and a Raspberry Pi 5. For the retrieval robot chassis, we used a three-layer 3D printed design. This modular design helped create custom fit parts for our components. And here we have the evolution of our idea for this design. And then here we have a more detailed view of the third layer. So our third layer contained most of our electrical hardware. We had our Raspberry Pi 5, our motor driver, our buck converters, as well as our IMU. So as you can see, those two photos on the left show the initial drawing for that. And then on the right, we have the physical implementation. And then here we have the wiring. So we have the Raspberry Pi 5 over here on the right, and then all of the components that I previously mentioned here on the left.
So the ReceiverBot flowchart, which is shown below, shows the overall process that it goes through. So initially it talks to the launcher bot and tells it that it's ready. Then it will feed the ball. Then it will go into trilateration, where it will measure from one point, move to the next, measure again, move to the next, measure. It'll use those positions as well as the distance that it determined from the ball to figure out where the ball is and move towards it. Once it gets close, then it will use the camera to find the ball more precisely. Then it will go towards it with alignment, and then it will use the time of flight to grab the ball, and then it will return back to the original position to feed again when the launcher bot is ready.
The hardware for the soccer ball was very simple. All we needed to do was embed a Bluetooth sensor inside the ball. And to do this, we just cut the ball open, put the sensor in, and then stitched it back up. The hardware for the launcher bot consisted of two high torque DC motors, aluminum T-slot railing for the chassis, two 10-inch linear actuators for angle control, two dual channel motor drivers, a 12-volt battery, 5-volt buck converter, 7-inch touchscreen display, wooden paneling, 3D printed ramp, and Raspberry Pi 5.
To give a little bit more insight as to how the design for the launcher robot came about, we started off with focusing on the motor design and being able to launch properly so that we could be able to test along with the software team. Um, to supplement that, we opted for aluminum framing, which was quite sturdy to prevent any sort of kickbacks or any sort of flexing from the launching mechanism. It was also very cost effective through the Clemson University department, the ECE department, and they also had T-slots on it, which made it very simple to 3D print certain aspects of the chassis and slot them into the railings so that it was very easy to work with. One example of that is on the bottom right picture. There's a ramp that is 3D printed and slotted into the railing, and that's how it's held in. To build on that, we also have 3D printed chutes and guide railings to be able to lead the ball in for the launch. We also have wooden paneling along on the outside of our chassis. It helps conceal all the wiring inside. As you can see on the right, the picture on the right, it's lit up through the guide rail, through the aluminum railings and concealed from the user. So it all leads into the Raspberry Pi 5, into motor drivers that control the linear actuator and the high torque RPM motors, as well as our 7-inch display that holds our GUI. To speak a little bit more about the linear actuators, they're 10 inches and they are used for our angle control, quite sturdy to hold the heavy weight of the chassis. And we have foam stoppers at the bottom that help prevent any sort of knockback, or if we're outside in outside terrain, we have a better grip. And lastly, just wanted to touch on the component wiring of the launcher robot. Starting on the left, we have a 12-volt battery, which leads into a fuse to protect our power supply, into two dual channel motor drivers, one for the DC motors, the launching mechanism, and the other is the linear actuators for the angle control. Another part that's being fed into the is the on the right is the buck converter, steps it down from 12 volts to 5 volts to power the Raspberry 5. And Raspberry Pi 5 also powers the touchscreen display that holds our GUI.
The LauncherBot flowchart, which is shown below, shows the user input, which is angle, speed, launch, as well as the weight. It then will communicate with the receiver bot, and then it will tell it when it's ready. Then it will start the countdown, move to the set angle, and then when the ball is fed by the receiver bot, it will be told, and then it will tell the receiver bot to go find it. The receiver bot will go, and then it will all return back, and it will then restart the process again to launch it. And then here is the full demo. So here you can see the launcher's GUI, and here I'll change the angle to 5, and then I'll change it to 10, and here we can see that the angle of the launcher is changing. And then I can also change the speed of the launcher. So I'll set this to around 95, and now I can set the launch count. So I'll set it to just one launch, and I'll set it to launch in 15 seconds, and I'll start. Now that it starts, the receiver bot will move back, entering feeding mode. And then you can see the countdown, 7 seconds left. And then once that countdown ends, you're going to see that it starts to speed up. And once it speeds up, then it would tell the bot, and the bot will push it in to feed the ball. Now I'm just going to move the ball off to the side. And then the receiver bot will move backwards and start doing trilateration, so it's in the first position. So we have it set to turn 120 degrees, so we'll do 3 different measurements, one at 0, one at 120, and one at 240. And then whichever one is best, it found that the best one was at 240. It'll measure 2 more times here for a total of 20 measurements in it. And then it'll move to the next position, do it again, it'll move to the next position, do it again. Once it moves to the third position, it will compare all those to try to trilaterate where it is. So you see now it's going to third position. It moves 10 feet between each, so it started at the original position, moved 10 feet to the right, then 10 feet towards where the launcher went. And now what it will do is it will take that and determine that it knows that the ball is that way, and then once it moves this direction, it will start to look for the ball. And here it sees the ball, so it will enter grab mode, which now it's using the time of flight sensor to detect how far away the ball is. It's moving closer, and once it gets close enough, it'll grab. It will confirm that it grabbed by moving slightly, and now it will return home. Once it's returned home, now it enters the alignment. So it's using the purple circle there with the camera to align the ball. Once it's aligned, it'll move back into position to be close, to be ready to feed again and launch.
So to discuss the results a little bit more, through the video you just seen, it showed the fully integrated process of our robot, as well as a couple successful results when some environmental hazards were reduced. And one thing that came out of this is that the team, as a team, our strength was setting the realistic requirements that we're able to, just collaborate together and achieve. I think our team did very well in that aspect.
So some of the challenges as well as bottlenecks that we had during the project was with the retrieval bot, we had uneven surface, which caused issues with the back swivel, which would deviate the driving path. We also had to determine what the best arm design would be to avoid snagging on the ball. And then we had ball detection issues, mainly trilateration and camera, depending on our tested environment. The launcher robot had issues with the chute, which ended up having a too sharp of edge. We were able to sand that down to make it feed better. And then the linear actuator is extended at different rates. We then used Python to adjust that through software and fix the issue. And then the ramping system wasn't completely flush when nearing the max angle, which we will work to fix.
Future directions for this project include further increase the ball retrieval speed and accuracy, smoother ball entry to the launcher by using bearings on the guide arm, improve airflow through the retrieval bot, improve the aesthetics, and invest in higher RPM and torque motors. In conclusion, we were able to use all the concepts and components above to create an automatic soccer ball launcher and retriever. The launcher bot successfully launches the ball while the retriever will locate, grab, and return the ball to the launcher to start the cycle over again. Thanks everyone for watching the presentation.